Hey everyone, you're listening to the Simple Electronics Podcast. I'm your host, Dan, from the Simple Electronics YouTube channel. This episode is brought to you by viewers like you. So if you want to support the show and you like what I'm doing, go to patreon.com/simpleelectronics. And even if you stick around for only 1 month, you are making a giant difference. Failing that, you can always just share my content in the relevant places, come to the live streams, or just leave comments on the videos or reviews on the podcasts. So getting started, well, you might hear that my voice is a little raspy again, and that's because I have started what could be my last college contract forever. For those of you who don't know, I got a college contract not to teach automotive because the program was destroyed, but to teach computers and math to would-be machinists. So I just have a small contract to do that. However, I'm teaching both classes on the same day. So I have 6 hours of lecturing to students, and so on a single day. And so that means it does wreck my voice a lot. So I was doing progress, but if my voice is a little bit raspy, like you might hear it on that word right there, well, you'll have to forgive it because this is essentially my most important income is to be a college professor. Not in the business of saying no to that. And so, voice is a little bit raspy, but we're going to get through it nonetheless. So for today's podcast, maybe it's time to lecture you folks a little bit. Obviously, just kidding, but I decided to go through a couple of concepts that I've sort of had in the back of my head for making educational type videos and electronics about topics that affect us as electronics hobbyists and experts alike, but that hobbyists don't really get a good chance to interface with. It's not really something that you need to know. It's more like concepts that are nice to know. And to give you an example of what we're heading into, the first topic that I want to talk about is multimeter counts. So a lot of you have bought multimeters, maybe even you're buying multimeters for others as gifts, and you compare prices from one brand to another. You're interested in features, maybe you're interested in hand feel, you're interested in the probes, but most of all, you're probably getting shoved the statistic of counts, multimeter counts, front and center of the page, and perhaps you don't exactly know what that is. So I just want to start off by saying in my workshop here, I have multimeters that go down to 2,000 counts so low that they don't advertise the counts on the multimeter, and all the way up to, I believe my highest count is 200,000 counts, and that would be my Unity multimeter. I forgot the model number now. The UT8805E, had to look that up. So 200,000 counts. And I mean, just to give you the idea, is that the Kaiweets HT118E that I use all the time, that is a 20,000 count multimeter. I've got the O1 sort of like budget desktop multimeter, and that one has, that's the XDM 1042, I believe. I might have to correct that in the notes, I'm not sure. But that one has 55,000 counts. And our counts accuracy, sort of. So it's very complicated. First and foremost, probably the highest level idea of what counts are. They are the discrete steps that the ADC, the analog to digital converter, usually integrated into the multimeter, multifunction chip, like the front end chip, the chip that does all the processing in the multimeter. So it's the amount of steps that the ADC can display. Now, you got to be very careful because a multimeter has multiple ranges, right? When you check voltage, you typically have a 200 millivolt range, 2 volt range, a 20 volt range, a 200 volt range, and maybe 1,000 volt range. It depends on your multimeter, obviously. But each one of those ranges have access to counts. It's a little bit complicated, but typically when the signal comes in, it is run through a voltage divider, right? A bunch of resistors in series, and sampling between a pair of resistors gives you your multimeter its range. And so, for example, if you have a very low voltage, then you can read it directly from the input. That's not a problem. You can probably read up to 2 volts directly from the input. But if you're connecting to like a 1,000-volt source, that's a lot of voltage. There is no ADC out there that can take 1,000 raw volts and display, an output. So in that case, you would have the voltage divider. You can read, after, but let's say there's 10 precision resistors in series. Well, you can measure between the 9th and the 10th, and that'll give you, a 1/10 reading of your voltage. So in that case, that would actually be, still 100 volts. That's a lot. So there might be more, voltage division past that. But the multimeter counts is essentially how many steps your ADC can give you. Now, it's a little bit more complicated than that, but just think about it this way. If you have a 2,000 count multimeter, right? So that means you have 2,000 discrete steps between 0 volts and whatever your range that you're measuring in is. So if it's a 20 volt range, then you can have from 0 to 2,000 steps on a 20 volt range. That would be essentially 20.00. Actually, 0 counts as a count. So it would really be between 0 and 19.99 volts. So you have 2,000 discrete steps you can work with. And so a 2,000 count multimeter, a voltage of like, let's say 12 volts, like a very common automotive voltage, computers run at 12 volts, etc. If you sampled that, you would get 2 digits of precision, 2 digits of, precision, I guess, and in your multimeter. But I'm not talking about precision like it's precisely that measurement. It just allows you to subdivide your measurement with 2 digits. So that would be essentially a 2.5 digit multimeter, something like that. To get even more precise, you could drop down to the 2 volt range on that multimeter, 2,000 count multimeter. And then you have the same 2,000 counts. So you go from 0 to 1.999 volts. So you can have actually 3 numbers after the decimal. So that's perfectly fine, right? At the 2 volt range, you get quite a bit of resolution. But now imagine if you want to display more numbers after the decimal. You want to measure down to the microvolts. Well, in that case, you need a lot more counts. In fact, if you get, so this is a 2,000 count multimeter, if you get a 20,000 count multimeter, so that would be like the Kaiweets HT118E, then with, 20,000, which is quite a bit more, then you get an extra digit. So you can go up to 1.999 volts. So you get an extra digit. That's why they call it a 3.5 digit multimeter, because you have that last digit. Why is it a half digit? Well, I believe it's considered a half digit because you have the precision of 20,000 counts, and then it's plus or minus, a couple of counts, right? Because, and we'll get into why there's extra counts momentarily, but the point is that you get more resolution when you have more counts because there are more discrete steps in between each measurement, like each range, each discrete measurement. Now, what is pretty interesting is that a 12-bit ADC will give you 4096 discrete steps, right? Because it's 12 to the 2 to the power of 12. So that gives you 4096 discrete steps. So that's 0 plus 4095, steps. However, a 4,000 count multimeter will use a 12-bit ADC, but only have 4,000 counts. So where the heck do the extra counts go? Well, the multimeter chipset will use those extra counts for averaging. So it'll reject noise and it'll slow down the measurement in order to be a little bit more sure of what the measurement is. So a 4,000 count multimeter requires at least a 12-bit ADC. So if you look at something like the Unity UT8805E with 200,000 counts, you would need, I can't really do the math on the fly here, but you would need something like a 18-bit ADC. I'm not sure if they do really use an 18-bit ADC or if they stack two ADCs to 14-bit ADCs or something and do some magic in order to get to those numbers. But if you've ever priced out ADCs, you'll know that the more bits you have, the price starts climbing exponentially. And so when you're looking at a benchtop multimeter, something like the Unity, and it's like, whatever, $500, then you can understand how come this multimeter costs so much money. It's because the chipset has to be able to handle so many counts. The same reason why lab equipment gets very expensive very quickly. In order to get the parts needed to display with enough not only steps, but then accuracy, which we'll get to in a moment, the parts start getting very expensive. So now, is a 2,000 count multimeter useless? Absolutely not. It really just depends on what you're doing. Like, for example, in my shop here, is my 200,000 count multimeter necessary for everyday use? Absolutely not. The reason to get more counts and especially to get more accuracy, which we'll get to in a moment, the two are related, but they're not the same. But the more counts is necessary to check the counts on a lower count multimeter. So, for example, the XDM 1042 OON multimeter that I have with 55,000 counts, I won't really be able to test, its accuracy or its capabilities without having an extra digit to play with, because the last digit of your multimeter will more than likely round up or down. And then on top of that, the last digit has a couple of digits of play, usually a couple of counts of play up and down. So you do need something with more precision or more numbers in order to compare values with a lesser multimeter. Like, I would love to test the UT8805E down to its last digit, but unfortunately, because it's a 5.5 digit multimeter, 200,000 counts, I would need a 6.5 digit multimeter. Let me just check really quick what's the minimum amount of counts for that. Looking really quick around the web, I found a Keysight article here that will tell you that a 6.5 digit multimeter will need 2 million counts. So that is quite high. So just for argument's sake here, 3.5 digits is 2,000 counts, 4.5 is 20,000, 5.5 is 200,000, and 6.5 is 2 million counts. So just to show you there, the actual amount of counts goes up by a factor of 10. Essentially, when you add an extra digit, it's an order of magnitude. And please excuse the lack of polish on this knowledge. This is all stuff I've been slowly researching over time. And in fact, most of these topics are really in the word vomit section, where I just, found some sources, jotted some stuff down, but I haven't gone through and done a polishing pass. So that's why these things are a little bit more haphazard. So here's the question now. Is counts, or do counts equal accuracy? Well, yes and no. So first and foremost, the overall final accuracy of your multimeter depends on how it was calibrated at the factory. However, a multimeter with higher counts will typically use higher end chipsets that are more temperature stable and which are more expensive, which means the product is more expensive, which means typically it'll go through a better calibration path. So if you're buying a multimeter that costs $10,000, but that multimeter is known to be inaccurate from the factory, probably won't sell a lot of those multimeters. So they tend to be from either higher end brands or simply higher end versions of brands that make even low end to high end models. So the Unity, for example, you can buy a Unity multimeter for like $40 on AliExpress, something like that. However, the one I have here, the 8805, is a higher tier product. So not only does it have 5.5 digits, but it also is factory calibrated with a traceable certificate. So yes, it kind of relates. You can sort of say the more counts in a multimeter, the more precise it'll be. But the other side of that is the higher the resolution is. So if the absolute accuracy doesn't matter to you, like let's say you have a device that is discharging a coin cell and the absolute voltage of the coin cell is not important to you, but more important is the rate at which the coin cell is depleting. Then you need something with a lot more counts because you want to be able to read those discrete levels. Like every 30 seconds, it's dropping, 1 millivolt or half a millivolt or, 1 microvolt. So it doesn't matter that your measurement is actually 100 microvolts off from what the battery actually has in charge. However, it is very important to see the rate at which it's discharging. So in that case, you really do want something that has a lot more counts in order to accurately determine how many volts it's dropping for how much amount of time. So that is one example. I tell my students in the automotive world that multimeter accuracy is kind of a non-issue for us in the trade. A fully charged battery is 12.6 volts. And you can be off by 0.1 volts, 100 millivolts. It could be 12.6 or 12.5 or 12.7, and that won't really matter for most diagnostics. It starts getting a little bit important when the battery gets a little bit lower, but it isn't 100 millivolts that will prevent your car from starting when you're talking about open circuit voltage, right? So it really plus minus 100 millivolts, it doesn't matter. And in fact, most of the diagnostics that you do, open circuit diagnostics, it can be plus or minus 1 full volt without mattering. So in automotive world, do you need absolute accuracy to be 100%? No, not at all. Not for automotive. For electronics, though, it does matter quite a bit. And I would argue that decent quality multimeters that are decently accurate have gotten so inexpensive that I think if you're trying to gear somebody up for electronics, I think there's really not much excuse to spend $5 or $10 more on something that has a good combination of a lot of counts and a lot of precision, or accuracy, I should say. I've been using accuracy this whole time. So if you think about it, the Kaiweets HT118E is a fantastic value for money. I think it's $50 Canadian, and you can find it on sale for cheaper. You can buy them on AliExpress. You can buy the Habo test versions of them. However, I don't know if Kaiweets does a QC pass over them to calibrate them. I'm not sure, but I find those multimeters have a phenomenal ratio of price to counts and to accuracy. The overall accuracy is quite high. Another reason you would want a lot of discrete steps, a lot of counts, is when you are calibrating or when you're measuring your voltage reference standards. So if you have a standard, like here I have a voltage standard that is, I believe it's 2.5, 5, 9, and 12 volts. I think that's it. Maybe it's 10 volts on the other range. I don't remember now. It's really important to have enough digits, like measuring it with the 5.5 digit multimeter, in order to see its absolute precision, and then use that to test other multimeters. So the unity has been calibrated. You can take a measurement of the voltage standard at a certain temperature, and you can know that this is what this voltage standard measured. You can write that down to 5.5 digits, right? Your 5 digits will be good. Your half digit is going to be plus or minus some. And then when you go and test your chi-wheats on it, which is 4.5 digits, then you can see the absolute accuracy of your chi-wheats compared to your standard that was measured with the unity. So it's kind of like you need that combination of counts and accuracy, but I believe they are both, two sides of the same coin. When you're chasing precision, you need both absolute accuracy and enough counts for it to matter. What do you think about all this? If I made a video covering these points, do you think it's accurate enough, or am I missing something? Let me know in the comments below. Next subject up is definitely one that I don't personally think about a lot, and I know that a lot of hobbyists sort of tend to ignore as well, and that is capacitor ESR. So ESR is equivalent series resistance. It's essentially the resistance that a capacitor offers to the circuit, and it depends on multiple things. So this is not like an aspect of a capacitor that you specifically design for. This is usually a negative thing brought about by the capacitor's construction, its electrolyte, its leads, its package type, its type, its construction, everything. So essentially, we are taught to think of capacitors as capacitors. So essentially, they're just a little reservoir of electricity, and you tend to put them close to MOSFETs or ICs or stuff like that. When there are rapid switches on and off in your system, and it filters out the little spikes, it allows, your microcontrollers not to brown out because they're little sort of reservoirs of electricity. The issue is at different frequencies, the equivalent series resistance changes, and it typically decreases as frequency goes up. The way I remember this is if you put a capacitor in series with a load, whatever, in your circuit, if your circuit is pure DC, your circuit will not turn on, right? Because capacitors block DC. But as your frequency goes up, so you could say DC has a frequency of 0, and then as your frequency goes up, that infinite resistance that your capacitor is showing to your circuit will decrease and down and down and down as your frequency, increases. So what is interesting about ESR is that it is a not often tested value in a circuit. So I see a lot of YouTube channels. Joey Does Tech is one of them, but Scott, the Def Bomb, will do some repairs as well. But there'll be a whole bunch of people doing electronics repairs, and typically they will test capacitors. Capacitors are very common failure mode for electronics, but they'll test their capacitance mostly. Although I do see people that are more apt at fixing things like Scott, for example, they would probably also test ESR, but a hobbyist like me probably wouldn't think to test ESR. And in fact, hobbyists like me are quite lazy. And so if I desolder a capacitor to test it, I won't bother testing ESR. If I've desoldered it, I'll just solder a new one on. That's just my philosophy as a hobbyist. But, in situations where you have very precise capacitors or non-standard capacitors that you would have to order replacements for, it would be a very intelligent thing to test the ESR, because as capacitors age, their ESR might increase. And think of it this way: if your capacitor has a higher than spec ESR, when it comes time to dump its reserve of energy into the circuit, like let's say there is a transistor turning on and off very, very quickly, and there's sort of like a voltage drop in the PCB trace that is supposed to be handled by the capacitor that's right next to it. If the resistance goes up in that capacitor, that means that its ability to supply voltage or to supply power will be harmed, because if you think about it, you can't get away from Ohm's law. When you increase the resistance, you decrease the current. There's no way around it. And so a higher ESR capacitor won't be able to dump current into whatever device needs it as effectively as it would have before. And even worse than that, it won't be able to absorb current. It won't be able to take current in as fast as it did before, because again, it has an equivalent series resistance that is much higher than it was spec'd to. And it gets worse than that, because temperature can affect ESR. So ESR can increase as temperature goes up. But here's the problem. If the ESR goes up, that means it is acting as a larger resistor, meaning that its charging and discharging will be across a larger resistance, which means that it'll dissipate more heat, which means that it'll heat up and increase its ESR, and so on and so on. And so you can see how when electrolytic capacitors get old, they tend to pop their lids. They will boil the electrolyte in it. And that's why they have those score marks on top of electrolytic capacitors, because they'll literally build pressure from that heat, and that pressure has to go somewhere. And if it's not let out, then you get what you see on Electroboom's channel. He uses capacitors to make his explosions because they are spectacular. In fact, if you looked at Electroboom's latest video where he moved out of his place, you can see on his ceiling, he shows you the impact craters from the capacitors he uses to explode in his videos. It's a pretty crazy thing. So your capacitor getting old and getting increased ESR will cause a snowball and increase ESR even more, which will increase its temperature, and so on and so on. The other thing to note is that power supplies, like every single power supply design, has capacitors in it. The point is to smooth out either the switching from your switch mode power supply, or to stabilize your linear power supply, or to smooth out the diodes, the rectifier section of a AC to DC power supply. Regardless, every power supply has capacitors built in. If those capacitors have higher ESR, then what happens is they charge and discharge slower than they should, and that means that your power supply now gets a ripple. So either the switching noise or the bumps of the tops of the sine waves will now show to your micro. If your micro, or whatever your project has, doesn't have a stable input voltage, it can then do false triggering, because if its voltage isn't stable, that means its ADC isn't stable, which means it won't read signals properly and can go to the extreme of like browning out even in some cases. So ESR really does matter. And the interesting thing about this is that you could have a capacitor that looks entirely normal, but just has a higher than spec ESR, and your system could be not working, not functional, just because of that. So that is very interesting and a little bit underserved in the hobbyist electronics community. One last note about this. I would just check my notes in between statements to make sure I've covered everything. But ESR, how to test it. So you can't use a regular multimeter. You need an LCR meter. An LCR meter is a multimeter made specifically for testing things like, you know what? I'm not going to enumerate them because I don't have them written in front of me. But one of the things it does test is ESR. So it tests all sorts of like secondary aspects of common components. Like it'll test inductance, it'll test capacitance, it'll test ESR, it'll test all sorts of things. But one of the things is ESR. So you need one of those, but you'll have to be careful because the way that you put your capacitor, the way you hook up to your capacitor will affect its ESR and it will affect its capacitance. So you got to be very careful when dealing with that. Another thing is that there are specific low ESR capacitors. So things like electrolytic capacitors tend to have a higher ESR than something like, let's say, a film capacitor. But there are electrolytic capacitors that are specifically low ESR rated electrolytic capacitors. So something about their construction, their electrolyte makes it better suited for tasks where, low ESR is required and you need the higher capacity of an electrolytic capacitor. There are a couple things you can do to get away with a slightly higher ESR, like, for example, installing two of the exact same capacitor in parallel rather than one should, quote unquote, should give you slightly lower ESR. In fact, we can test this in a video or in the live streams if you guys want, because I do have an LCR meter. But if at all possible, you should just buy the specified capacitors. So generally, low ESR capacitors will be more expensive, and that would be the reason that maybe you see some manufacturers using two capacitors in the place of one. So if I can leave you with one thing is test your ESRs. That could actually be another reason why you got such a bargain on your AliExpress capacitors. They might fit every single spec that they've been manufactured to, except the batch had higher ESR. And so instead of being thrown in the trash, or maybe they were thrown in the trash, then they were picked out of the trash and sold to you for pennies on the dollar on AliExpress. So just one of the things we don't really think about when we're getting a bargain on electronics components. Interesting, huh? Since we're on a topic of ESR, which can ruin your day, another topic that I've been researching is battery internal resistance, right? So this is the resistance that a battery has as a feature or a bug or whatever you want to call it of its actual internal construction, of its chemistry, etc. So every single battery, as a consequence of it existing, has an internal resistance. Does internal resistance of batteries matter all the time? The short answer is no. As you know, typically the more current you draw, the higher that your I squared R losses are. So, the higher your resistance affects your circuit. If you're pulling like 1 microwatt, having an ohm of internal resistance probably won't matter, right? Or half an ohm or whatever it may be. It probably won't matter if you're pulling in the terms of, microwatts. You think of a watch, essentially. you're only powering like a crystal oscillator. That's about it. And the watch will run on a coin cell for like a short eternity, essentially. It lasts almost forever. Same thing if you think about the AAA cells that are in your TV remote. How much power does it really take to flash an infrared LED a couple of times to send a signal to your TV to turn on or to volume down or whatever? Those cells, they typically last years. However, the problem becomes exacerbated when you pull more current. So when you have a device that requires a lot more current, then what happens is that internal resistance will chew up a lot of the open circuit voltage, and your device might not be getting all of the voltage that you need for it. I think the best example of this is the NRF24L01 modules. Now, when they first hit the market, tons of people made videos on them, and a lot of people essentially were having issues with them. And the issues turned out to be when you power it from a breadboard, the resistance in the connections on the breadboard would cause a voltage drop when the NRF uses a relatively high burst of energy to transmit or to receive, mostly to transmit. And that was browning out the chip, causing it to reset. Same thing if you used too small of a cell. If you used like a 9-volt battery with a linear regulator, sometimes your 9-volt battery would get low voltage and brown out the source. Same thing if you use like a bunch of coin cells or whatever. The internal resistance of those power sources were much too high that when the NRF decided it needed to pull that current, the internal resistance dropped the voltage inside the cell, which then browned out your chip. So a lot of people recommended to put a capacitor between 2 pins of the NRF24L01. And, therein lies the ESR problem, which is while researching all this, I'm wondering if a lot of my problems stem from me using relatively large electrolytic capacitors for my NRF24L01s and them browning out. Who knows? I'm probably going to test it on the live stream because those capacitors are soldered to the chips. So yeah, that'll be interesting. But regardless, we're talking about internal resistance of a battery. So in high current applications, so this is obviously near and dear to my heart because of my NRF24L01 problems, but also I'm an automotive guy. So something that takes a lot of current, like a car's starter motor, can draw, 400 amps for, a millisecond or so, but still 400 amps. You can get a situation where your car won't start because of the internal resistance of the battery. So really interesting here, especially as we are moving towards EVs and stuff. Lithium ions, for example, lithium ion cells, their internal resistance will actually increase in the cold. Have you ever heard that people get less range in the cold with their EVs? Well, that's because the internal resistance of the cell is higher when it's cold. If you think about it, a battery is really a controlled chemical reaction, right? A lead acid battery is sulfated acid, sulfated liquid, where the sulfur has to migrate into sponge lead of the, I believe it's the negative plate. I don't remember. But anyways, it migrates from in solution to in the plates. And that process is slowed down by the cold. Well, it's the same thing with lithium ion cells. To actually get those ions to get moving, they don't want to move as easily in the cold. And so that is why in the cold you get less range on your EV. It's also the same reason why your cell phone doesn't stay charged as long in the cold, why your power banks don't perform as well in the cold. If you are a person that deals with RC vehicles, like I have the snowspeeder, for example, you can get a lot more speed out of your RC vehicle if you preheat the batteries. Really cool concept. Just to give you like an idea, okay, of like general knowledge for how much internal resistance is in whatever batteries. Now, this is pulled from a couple sources, so it's kind of a big range, and I haven't verified. I haven't tested it on my workbench here, so just take it as a relative measurement. Double A's, so double A cells, alkaline, between 100 and 300 milliohms of resistance. So if you think about that, that's still quite a bit, a third of an ohm, up to a third of an ohm of resistance. And it increases in resistance as the cell drains, right? You probably watched Dave Jones' Batteroo or Batterizer videos where they talk about the discharge curve. Well, it falls off a cliff when it gets discharged. Well, that's what it is. The internal resistance will increase. Now, nickel metal hydride AA's with the low self-discharge chemistry, that's between 30 and 50 milliohms. So you can pull a relatively high amount of current from those cells, which is a little bit scary because some, like the cheap AA's you get at the dollar store, AAA's you get at the dollar store, you can pretty much short them out with one of those cheap breadboard jumper leads, and they won't do anything. But the nickel metal hydride ones, though, the rechargeables, you do that with one of those breadboard leads, and that lead will start smoking, especially since those breadboard leads are mostly steel now. They're not even copper anymore. They're like steel wire having a higher resistance. So you're really creating, you're essentially creating an incandescent light bulb out of that stuff. So you can short something like a coin cell because it has relatively high internal resistance, but don't do it to a nickel metal hydride AA, and probably not a lithium AA. So a lithium ion, like 18650 essentially, can be as low as 10 milliohms, but it can be high as 70 milliohms. And of course, they are going to increase their internal resistance when it's colder, and they're going to increase their internal resistance as they age. But a really interesting thing, if you used to watch AVE videos like I used to, he opens power tool batteries. He used to open power tool batteries all the time. And in power tool batteries, there were typically lower capacity cells in those batteries. And it turns out that those lower capacity cells were chosen not because they were cheaper, but because they had lower internal resistance for the most part. Really cool concept. But again, they will increase in the cold, and they do increase as they age. So your old battery that you got with your drill 10 years ago, it may charge up, no problem, but you'll notice that it won't run your drill for as long as it used to. And that's completely normal. That's part of its aging process. Now for lithium polymer batteries used in RC vehicles, like I bought some for the drone here, the drone that I need to finish building, they can be as low as like 2 milliohms, but usually around 10 milliohms. So very, very low internal resistance. And same thing with the lithium here. The reason why these cells are so dangerous, or these batteries are so dangerous, is because of the low internal resistance. If you short something, you will create a lot of heat very quickly, and lithium fires are hard to put out. So keep that in mind. Now for your car battery, this will depend, right? If you have a very small car, like my wife has a Honda Fit, tiny, tiny battery, probably more around 15 milliohms of internal resistance. But for something big like a truck, especially a diesel truck, a really big battery, you'll probably get as low as like 2 or 3 milliohms. So lots of current that's able to come out of these batteries, and very purposely. I mean, if you open up one of those lead acid batteries, you'll see that there's massive terminals, big chunks of lead in between the cells to create, to, put them all in series. And so really beefy things. And so that's why they can deliver so much current. Another interesting fact about internal resistance is that it's not just down to only the chemistry of the cell, right? An alkaline AA cell and I think it's a 14500 lithium ion cell, they can have the same sort of construction, but the chemistry means that the lithium cell will have lower internal resistance. But it's actually the physical construction of the cell that will affect its internal resistance as well. So the most obvious example of this is in RC car cells. Typically, when you compare two qualities of cells, they usually have like a C rating. So that C rating is how much instantaneous discharge you can get from them, how much current you can get from them as a factor, as a ratio of its capacity. And so you can essentially buy, let's say, a 3-cell, 5 amp hour pack. So that would be a 11.1 volt nominal with 5,000 milliamp hours of capacity. But you can buy them in 25C, so it can discharge 25 times 5, so 125 amps maximum instantaneous. You can buy them in 50C, so 50 times 5 amps, so that would be 250 amps. You can buy them all the way up to something like 125 or 150 or 200C. And if you grab the same manufacturer, the same cell size, like the same cell voltage and the same cell capacity, the big difference between the C's, right, the amount that it can provide in current instantaneously, is typically the surface area of the cell. So you can have a cell that has the same capacity, but if it has a higher C, it'll typically have a larger surface area, have a larger footprint. It won't be as thick. It'll be, bigger in the length and width department. So the more surface area, I think that's how it works at least, is the less, the layers are compact together, the more current it's able to deliver. It's a really cool concept because I suppose that you scrape those ions, right? Those ions come off the entire surface towards the wires in one direction, and that makes it flow easier, I guess. I mean, there's got to be some sort of quantum rule why that works. I'm not quite sure, but it does work. In automotive, you'll see that the electrode plates have more surface area. So they're bathed in maybe the same amount of electrolyte. Maybe it's it's a gel battery where the electrolyte is actually a gel solution that is just that's kind of stuck to the electrodes. But the bigger those electrodes are, the more of the sulfuric or the sulfur ions can go from liquid or from the electrolyte onto those plates. The more room on those plates there are for those electrons to, come in, then the more current you can pull from, a similar sized battery. So really interesting to see that relationship. And in fact, my research is showing that typically lithium chemistries, the more the capacity of the cell, the lower its capability of delivering current. And I know that for charging, right, a lithium cell, you can charge very quickly when it's almost dead, but when it's completely full, it kind of slows down. And the reason for that is it's sort of like you can think of the electricity going back in the cell a little bit like a parking lot, right? So a car going into a parking lot, when the parking lot is empty, it can just come in and park anywhere it wants. But when the parking lot is nearly full, let's say 80% full, then the electricity needs to go around the cell looking for a parking spot. It takes more time. And that's why, it takes longer to charge a fully charged or almost fully charged lithium cell. But it seems to be that the more capacity there is, the lower its discharge rate is. Now, I don't know if that's a function of its C rating, right? So technically, since the discharge is sort of linked to its capacity, maybe it's just a mathematical function and it's all the same. But it does tend to be that when a cell has more capacity, it's not able to discharge as quickly. Don't know why. I haven't gone that deep in the research. Well, let me know what you think of these 3 topics. So we did multimeter counts, we did capacitor ESR, and we did battery internal resistance. I think they are underserved topics in the hobbyist electronics world, and I really like your feedback if any of that made any sense to you at all. Now, mind you, this wasn't a polished look, right? I'm not at that point yet where it's all polished and ready to go into a video. I'm just essentially sharing with you my raw notes on the subject matter. So before we finish the episode today, I do recommend you come to the next live stream, which should be at some point in the next couple days, or in the next at least in the next couple weeks, because I've got 2 new PCBs sent from PCBWay, the sponsor of my channel, but not this episode. And I'm going to be building them up. And one of them, which is the F1 starting lights, will require a lot of CAD work and a lot of software work. So if you guys want to come in and encourage me on the live stream while watching how the sausage is made, so to speak, let me know. I should, if everything goes well, and I'm finding some wood here to knock on, I should have a guest for next week, so it should be a little bit easier on my voice. I still have 3 more weeks of teaching, and then my voice should be able to recover after that. But now it's getting kind of late, so I got to get this into the editing booth. So I want to thank you all for listening, and I will catch you on the next one. Don't forget, if you want to support, patreon.com/simpleelectronics. Thanks for listening, everyone.